Well, hello, ladies and gentlemen. So this is lecture number 3 for thermodynamics. We're going to have a number of topics today. We're going to finish off the initial introduction to the course. That's the plan for today. And then we're going to move on to properties of pure substances. So topics. We're going to finish off the introductory part of the course by looking at processes. In particular, we're going to look at 3 kinds of processes. Isobaric. We'll talk about what this is in just a moment. Isochoric. C-H-O-R-I-C. Isochoric. It's not choric, it's choric, isochoric. And then we have isothermal processes. So we're going to look at these 3 processes, and then we'll do an example. And then we will move on to properties of pure substances. So properties of pure substances. In the notes, that's chapter 2. In particular, we're going to be looking at material phases. Material phases. We're going to be looking at the phase diagram. And then we're going to do an example. Okay, so that's the plan for today. We're going to finish off the introductory material and then move on to chapter 2, which is properties of pure substances. Okay, so let's change the camera here. So let's go over processes. So first of all, what is a process? What is a process? A process is the path taken by a system through a number of states. The path taken by a system through states. Okay, so let me give you an example here. Let's say we have a piston cylinder device. What is a piston cylinder device? It is a container with a movable piston, in it. And inside the container, we have some sort of gas or some kind of material, let's say. So this is a piston cylinder device containing some kind of gas. And the piston can move up and down, okay? So it's a gas trapped in a piston cylinder device. So let's say this is state 1. And I have some, temperature T1 and volume V1 inside of this cylinder. Okay, my system, by the way, is the gas. This is my system. System is the gas. And then I squeeze down the gas in the piston cylinder device. So the piston is now moving downward. So here's my gas again. And this is state number 2. So I have a T2 and I have a V2. And now I'm going to squeeze down the gas even more. And this goes down to state 3. So now the piston is even further down into the cylinder, and I'm squeezing the gas down, and I have a temperature T3 and a volume V3. A little bit hard to see there. So this gas is being squeezed, and I can plot the process. The process that's going on. Temperature, volume. I can plot the process. I start off with a fairly high volume. So here's V3, here's V2, and here's V1. So volume is decreasing. When you squeeze a gas down, usually, not always, but usually, it heats up. So if you were to squeeze a gas down, it should heat up. So in theory, this should be, let's say, T3, T2, and T1. Temperature is going up. I'm sorry. T1, T1. Hold on a second. I've got this backwards. This is V1. No wonder this is screwed up. This is my initial volume, V1. It's at a maximum. V2, and then V3 is my final volume. Temperature T1, let's say it starts off cool, and then I squeeze it down, and it starts getting warmer. So I can draw the path or the process through these states. I guess let's get this looking right. So here is T1, here is T2, and here is T3. Move things around just a little bit. There we go. Okay, so the system is starting off at state 1, moving through state 2, and arriving at the final state, state 3. So this is the direction the system is going. So on a TV diagram, a temperature volume diagram, I'm showing the process as we go from state 1 to state 3 through an intermediate state, state 2. And the path, i.e. the process, is given by this line right here, okay? So process is a path taken by a system through states, okay? So the system is moving up and to the left on the TV diagram. So that's an example of a process, okay? Now there are a lot of different kinds of processes, and some of them come up over and over and over again, and it's good to give them a particular kind of name. There are many kinds of processes that come up, that crop up over and over again when you do thermodynamics problems, and so they're actually given their own names. Let's list a few of these processes. So common processes. Common processes. I'm going to list 3 today. There's actually more, but we're going to start off with 3. As time goes on and it becomes important, I will introduce additional processes. So, common processes. Number 1, isothermal. Isothermal process. What is an isothermal process? Well, iso means constant. What do you think the word thermal refers to? Well, if you thought temperature, then you're right. So isothermal refers to temperature or constant temperature. Constant temperature. So isothermal process is a constant temperature process. In terms of a diagram, The isothermal process can be viewed, let's say we have again a TV, temperature volume diagram. So we have some kind of a piston cylinder device. So here's our system. Okay, so here's our system. I don't know what it is. It could be a gas, it could be a liquid, it could be, who knows what it is. The point is, this system goes through some kind of an isothermal process. So I can plot the isothermal process. Let's say we start off at state 1 and we go to state 2, and this is an isothermal process. That represents a horizontal line. Notice temperature. T is constant. Temperature is constant for the isothermal process. So we're starting off at some initial volume, V1, and we are going to a final volume, V2, and we're doing it isothermally. Okay, constant temperature process. So that's our first common process that has its own name. What's another process? Well, another process is isobaric. Isobaric. Well, we know the word iso means the same or constant. So what might baric refer to? Well, I'll let you think about that just for a moment. Remember, there's a unit, a particular metric unit called the bar. What does a bar in metric refer to? I'll let you think about that for a moment. So number 2, we have isobaric or isobaric. Okay? And again, iso means constant. Constant. So what quantity has a unit of a bar? If you thought pressure, you would be right. So isobaric refers to pressure or constant pressure. Constant pressure process. Constant pressure process. So again, I could have a piston cylinder device of some kind. I could take a gas or something. And instead of having temperature and volume here, I could have pressure and volume. So on a PV or pressure volume plot, isobaric processes will be horizontal processes on the plot. Let's say again we have some sort of a piston cylinder device. Okay? And we have some kind of a gas or some kind of material in here. So this is our system. How could we get an isobaric process using a piston cylinder device? Well, we could stick a mass out here and stick it right on the surface. I could put a mass right here resting on the top of the piston. And so that would apply a downward force on the piston and pressurize the system. Okay? And again, I haven't mentioned this yet, but I am assuming that the piston moves up and down freely. So here's the piston. I'm assuming the piston moves up and down freely in the cylinder. In other words, frictionless. Frictionless piston. Frictionless piston. Okay? There's no friction between the piston and the cylinder. And if I stick a mass on top of the piston, that applies a weight and produces a pressure inside of the piston cylinder device. So it will be a constant pressure. Okay, it'll be a constant pressure due to the presence of the mass. So let's say I let this system expand. No, I'll let this system be compressed. So this is state 1 and state 2. Kind of running out of room here. Let's do what I can. This is state 2. I'm going to compress this system. Maybe it's a gas, who knows. So again, here's my system. Could be a gas system. And again, I got my mass here. That's applying the constant pressure. So I'm going to squeeze down the system. And so state 1 will start out here with volume V1. So originally I have a volume V1. And I have some kind of pressure, obviously. And then I am going to isobarically compress the system. If it's a gas, then I'm compressing the gas, okay? So this is what the process looks on a PV diagram. So I'm compressing the system. I end up at state 2, which has a volume V2. And of course, the pressure is the same. So this is state 2, and this is my pressure, okay? Pressure is constant. Pressure is constant, okay? So the system is moving from right to left. There's the process, state 1 to state 2, along an isobaric path, okay? So this is a very common process. Isobaric processes are very common. They often come up in piston cylinder type problems, okay? Isothermal, not so much, but isobaric processes often come up for piston cylinder devices, okay? And you'll be doing some examples on that later. Let's do another one. Got one more process we want to look at. Very common, and that's isochoric. Isochoric, how do you spell that? C-H-O-R-I-C, isochoric. So number 2, isochoric process. Again, iso means constant or the same. Choric is actually a strange way to describe, or word to describe, volume. So isochoric process means constant volume. Constant volume, okay? Constant volume process. Now, what might an example of a constant volume process? Let's say we have a container, a rigid container. So rigid container, and it contains some kind of gas. So this is our system, some kind of gas or something, okay? State 1. State 1, I have, I don't know, some temperature T1, some pressure P1, and of course I have a volume V1. And now I'm going to add some heat. I'm going to add some heat to this gas contained in a rigid container. Look at what I'm drawing here. We're going to state 2, and we go to state 2 by adding heat. Look at the arrow. The arrow indicates I'm adding heat. So I'm going to put Q here. I'm adding heat, and I end up with state 2. So here's my rigid container, and now I have a temperature T2, a pressure P2, and of course I have a volume V2, which is equal to V1. It's a rigid container. Rigid container, no volume change, isochoric process. Rigid container, okay? So I'm adding some heat as I go from state 1 to state 2. I'm going to put a little subscript on here as well. Heat added from state 1 to state 2. 1 arrow 2, okay? So I'm adding heat, and the system is moving from state 1 to state 2 isochorically as I add heat. What do you think is going to happen to temperature or pressure? What's going to happen to temperature or pressure as I add heat to this gas in a rigid container? Well, it should heat up, so temperature will go up, and also if the container is rigid, the pressure should go up too. The gas wants to expand, but it's got nowhere to go. It's a rigid container, so pressure should go up and temperature should go up. So I should have, here's a TV diagram, temperature, volume. And so the process looks like a vertical line from state 1 to state 2, where I have a temperature T1 and temperature goes up to T2. So temperature is going up and the process is isochoric. Volume stays constant. So this is V1 is equal to V2. Isochoric, isochoric. Pressure is going up too. So let me put up the PV diagram, pressure volume diagram. Volume, so here is state 1, and I have a pressure P1, and I add heat, and pressure goes up to P2, and I end up at state 2, and of course volume is constant, so V1 is equal to V2. So that's what the processes look like. An isochoric process looks like on a TV and a PV diagram. Constant volume, constant volume. Now, before we finish here, I do have a little question for you. Gonna see if you understand what's going on here. Let's say I gave you the following process. Let's say I gave you the following process. I'm just going to throw this out here and say something about it. Let's say I have a pressure volume here. And let's say I have the following process. Here's state 1. And this is what my process looks like. State 2. Note that P1 is equal to P2. Volume, of course, is increased. So this is V1 and V2. So obviously volume's increased over this process. Note, P1 is equal to P2. Is this an isobaric process? Isobaric means constant pressure. The answer is no. This is not an isobaric process. Pressure is changing along the path. So it's not an isobaric process. Just because your starting and final value for pressure is the same does not imply automatically that it's an isobaric process. Okay? Here's another one. Here's temperature and volume. State 1. Around in a circle. Notice, I guess I can, so there's our volume there at the end. So I guess this is state 1 and it's state 2. We go along a path and we end up back where we started. So V1 is equal to V2 and T1 is equal to T2. So the initial and the final state are the same. We just go around in a circle on the TV plot. Is this an isothermal process? T1 is equal to T2? The answer is no, it's not a constant temperature process, so it's not isothermal. Likewise, is it an isochoric process? V1 is equal to V2. The answer is no, it's not a constant pressure process. A constant pressure, constant volume process. Constant volume would be a vertical line on the TV plot, and constant temperature, isothermal, would be a horizontal line on the TV plot. Okay, so none of these examples are iso anything. Okay, none of them are iso anything. Let's do an example here. Let's do an example involving processes. Okay, involving processes. Let's do an example involving processes. Example. By the way, before we get going here on the example, let me show you what is recommended on the homework and doing problems in thermal. I had that handout posted on guides to doing homework. Let me show you how that's done. Let me go to screen share here. Now what I have here, this is the notes. The handout is more or less the same thing as the notes. If you go to the very end of the notes, nearly the end of the notes, you'll see a section on this Appendix A, coursework format with example. So let's go over how the coursework or the homework is supposed to be done. So you should have your green engineering paper, put your date, the course, your name, and the page number. Page 1 of 2 or 1 of 5 or whatever it is. I suppose you can do it, the max pages could be for the entire homework or it could be for each individual problem. It's up to you. And then you have the problem statement. So you need to write down word for word what the problem statement is. Okay, so we know what the problem is. And then you put a nice black, thick black line right here. Okay, nice black line. And then right below it, you have a section called given. And in this section, you translate the problem into mathematics. What are you given? Okay? And then you have a section called find. What is it you were supposed to find? Give the symbols, give the variables for what it is you were supposed to find. The mathematical expression for what you were supposed to find. Okay? Then if there is any schematics that are involved with the problem, any pictures that are used or given, then you should have the schematics. And then you should have a section called assumptions. If you're looking up any data, if you have a system that's made out of a particular material and you need to get properties, we'll talk a little bit about this later, but if you need to get properties out of tables to do the problem, then you need to write down where you got the data from, where you got the properties from, okay? Any sources for the problem need to be listed in the assumptions. Also, any assumptions on the behavior of the system. We'll talk a little bit more about assumptions as we go along, but there is this assumption section. And then finally, we have the analysis section where you proceed mathematically through the problem, calculating, or eventually arriving at your solutions and your answers. When you're all done and you have numerical results, you box them up at the very end of your homework. That way, your boss, yourself, the grader, me, can look down at the very bottom of your work and see your answers, okay? Of course, we'll check how you got the answers, but the answers should be listed at the very bottom. Here's an example. Here's an example. You don't have to worry about this. This is a little bit complicated. We have a process involving air moving through a couple of devices. I see the word isobaric here. Don't worry about this reversible and all this other stuff. Here's a diagram. It's a TS diagram. S is actually entropy. We're not going to get to entropy for about 4 or 5 weeks, so don't worry about that. But you got a diagram. You've got a diagram indicating the process. You've got your givens, initial states, intermediate states. Any givens are listed here in mathematical form. The problem statement is given up here. So you should write this down, the problem statement, distill it into the mathematical form using the givens, indicate what variables or what quantities you're supposed to find. Apparently, we're supposed to find some temperature, T1 and T2 in this problem. Assumptions, you've got a list of assumptions, including sources for properties. So some properties are evaluated here. You see Moran and Shapiro listed, and a table A20 is listed here. So apparently we got some data out of a table A20, and that's indicated in the assumptions, all right? And then you've got the analysis, and you've got a bunch of equations. It looks like the first law, the energy balance, and you do a bunch of stuff and calculate your results, okay? So that is how I expect you to do the problems in your homework. So let's go over an example here. So let's go over an example involving processes. I'm not going to give you a problem statement. Let's assume there's a problem statement. I'm going to go immediately to the given, but I'm going to write problem statement. If you got a problem statement for the homework, you should write it down in the problem statement section. So I'll write some quotes in here, and I'll close it up. Now, what I'm giving you, I'm going to put a schematic up. I'm going to go right to the schematic. Right to the schematic here. I have a piston cylinder device going through a number of different processes. Okay, and this thing contains a system like some kind of gas. Okay, some kind of gas. So this is state one. So initially we have a volume V1, a pressure P1, and a temperature T1. And then I go to state two. The volume, I'm going to give you the process in just a minute. It looks like the volume remains constant. So this is state two. And we have a pressure P2, a volume V2, and a temperature T2. And then, running out of room here, it looks like the gas expands. So we're going to let the gas expand. Here's our gas. And this is state three. And I have a pressure P3, a volume V3, and a temperature T3. Let me give you the processes here. So we have a given section. Given. The initial volume, V1 for our gas. So we have a gas in a piston cylinder device. Gas in piston cylinder device. Okay, gas and piston cylinder device. Your initial volume for the gas, V1, is equal to 0.4 cubic meters. Okay? The final volume, V3, is equal to 2 times V1. Okay? So it doubles in volume, at least from the initial to the final state. The pressure, P1, is equal to, the initial pressure at state 1 is equal to 150 kPa. And pressure P3, that's the final pressure, is 350 kPa. Okay? Now, what are the processes? Oh, sorry. Let me stop sharing here. Sorry about that. Getting ahead of myself. Okay, so we have a piston cylinder device. It goes through 3 states. State 1 to state 2, and then to state 3. It's a gas or something in a piston cylinder device. Sorry about that. We have our problem statement. You'd write that out. And then I got my givens. Gas in a piston cylinder device. My initial volume is 0.4 cubic meters. My final volume is twice the original volume. My initial pressure is 150 kPa, and my final pressure is 350 kPa. So that's what's going on in this particular problem. Okay, let's, what are the processes? Process 1 to 2 is isochoric. isochoric process 1 to 2. You can kind of see that the piston isn't moving. And then we have process 2 to 3. That is going to be isobaric. Okay? Isobaric. Process 1 to 2 is isochoric. Process 2 to 3 is isobaric. What are we supposed to do? Find. Let's draw the process or find the process on a pressure volume diagram. PV diagram of process. We're going to draw pressure as a function of volume for process 1 to 2 to 3, okay? Process 1 to 2 to 3. Okay, so I'll tell you what, why don't I stick on the same board and I'll do the process. Oh, by the way, what are the assumptions in this particular exercise? Assumptions, I'll write it right here. I wish the resolution was good for both these boards together, but one at a time is pretty much maximum. In the assumption section on the homework, just put none. In this particular problem, just put none on the assumptions. We're not making any assumptions when we're doing this particular problem. Okay? So analysis. It just involves a plot. Analysis. Well, pressure, volume. First of all, let's put state 1. We know everything about state 1. We know the pressure and the volume. So let me put pressure and volume on the plot, okay, for state 1. So this is P1, which is 150 kPa. This is going to be in kPa. Okay? And volume is going to be in cubic meters. Okay, so we start off with 150 and 0.4 cubic meters. So this is state number 1. That's state number 1 right there. Okay, that's state number 1. All right. Now we're told process 1 to 2 is isochoric. Isochoric means constant volume. So I'm going to write right over here, V2 is equal to V1. Why? Because it's isochoric process. V1 is equal to V2, so it's an isochoric process. Okay, so V1 to V2 is an isochoric process. So that means volume remains constant, and we're moving up and down this line here, okay? Now the question is, what is P2? So this is V1. V1, which is equal to V2, which is 0.4 cubic meters. The question is, what's P2? How far do I go up vertically? How far do I go up vertically or down? I suppose pressure could fall. Where do I go vertically on this PV diagram? Well, the answer is, note that process 2 to 3 is isobaric. So P2 is also equal to P3 because it's isobaric process. Okay? So let's put P3 in. P3 is 350 kPa. So P3 is actually equal to P2, which is equal to 350 kPa. So here's 350. So state 2 must be right here at pressure P2, which is equal to P3, which is equal to P3, okay? So 1 to 2, that's process 1 to 2. We know P2, we know the volume, we know the initial pressure. It's isochoric, so it has to move on this vertical line. So process 1 to 2 is a vertical line from P1 up to P2, which is equal to P3. Process 2 to 3, let's draw that one. That one has to be along a horizontal line in PV space, has to be along a horizontal line. So the question is, what direction do we go? Is volume going to decrease or increase? Well, note, we're told that V3 is equal to 2 times V1. So V3 is 2 times V1, which is 2 times 0.4 meters cubed, or if you like, sorry, I'm running out of space. I want to do this all on one board. 2 times 0.4 or 0.8 cubic meters, okay? V3 is 0.8 cubic meters because volume is doubling from state 2 to state 3. So here is V3, which is 0.8 cubic meters, and the process is isobaric, so it's going to be a horizontal line. And this is state 3, okay? So that is the process. 1 to 2 to 3. That is the process. 1 to 2 to 3. The overall process, all right? So that's how you're supposed to do a problem. Of course, don't squish things up quite as much as I've done it here because I'm trying to get everything on one board, okay? Trying to get everything on the same board. Space it out a little bit better in your homework assignment, okay? Okay, so I think that's it on chapter 1, or introduction to thermodynamics. Oh, by the way, I have posted, let me see if I can find it here. I have posted, let's see, where is it? Let me see if I can find it. Posted on Canvas. Yes. Posted on Canvas. This is not it. Where is it? There it is. I posted on Canvas a document called Concepts and Definitions, Fundamental Concepts, Terminology, and Definitions. It gives written definitions for system, properties, state, process. Don't worry too much about some of this other stuff first. This thing called surroundings, isolated system. Don't worry too much about continuum. You can read these if you want. You can read these if you want. I'm not going to go through too much on this. But I have provided you with a document on Canvas that goes over and repeats some of what we've done for the concepts here, okay? Okay, I'm going to break this before we go on to chapter 2 here. I'm going to break the lecture.